Alright, so good afternoon. What we are going to do now today is dive a little bit deeper into the AXI bus, right? The ARM bus, which is specifically which was defined as by the company ARM primarily for use with their processors, but has since then been extended in certain ways and is also now become a very popular bus that is used for many different kinds of microcontrollers and microprocessors, right? Part of the reason for that is ARM very sensibly, I think, made the protocol itself an open protocol, and they didn't sort of say, okay, we are the only ones who are going to make use of it, which means that others can also implement it and make peripherals and devices that are compatible with the core bus. And like we discussed last time, the whole idea of a bus in this way is that once you have a master that is compliant with the bus, it can talk to any slave that is in turn compliant with the bus, and vice versa. If you are designing a slave peripheral, all you need to do is make sure that it follows the protocol of the bus in terms of how to respond to write requests, read requests, and so on, and as long as that happens, it will then be able to connect to any master that is compliant with that bus. So what does this bus compliance mean? What are the steps involved? What are the kinds of transactions? That is what we are going to look at in a little bit more detail today. So just a word of the background for the figures that I have used in this presentation. Pretty much all of them are from one of these two documents, either the AMBA specification. AMBA basically stands for the ARM, the Advanced Microcontroller Bus Architecture, right? And AMBA is what ARM first proposed for their system buses, right? The version 2.0 was in use for a very long time. It gave rise to a couple of different variants called the AMBA High Performance Bus, or AHB, and the AMBA Peripheral Bus, APB, right? And using some of the learnings from those implementations, from those buses, ARM then extended it and came out with version 3, which they called the AXI, the Advanced Extensible Interface, okay? And AXI 3 then led to AXI 4. Currently there is an AXI 5. The main point is each of those has been brought in for a specific purpose. They increase the functionality of the systems in some way or the other, or try and streamline certain kinds of operations, okay? These two documents are freely available from the ARM website. You can download them and look at them. I will also put them onto the Moodle so that you can take a look, but most of the figures that I have used over here are essentially directly from one of these two documents. So let us start with a generic picture of what a high performance bus based system looks like, right? So what we are essentially talking about is something like this. What we have is, I mean, of course this is defined by ARM, therefore they assume that what you have is an ARM processor, a high performance ARM processor as they call it, right? Alright, I don't think I need to use the journal application. If necessary, we will just switch to that later. So the high performance ARM processor that we have over here is any ARM processor, right? By ARM processor, what we mean is things that follow the instruction set defined by ARM. The other peripherals that you can see, this, what we have over here is something called the AHB, right, which is the AMBA high performance bus, and on the right hand side you can see that there is something called the APB, or the AMBA peripheral bus, right. So the expansions of those are basically given below over here, right. So the AMBA high performance bus, like we discussed last time, is used to connect those peripherals that have high performance requirements. The most obvious one is the high bandwidth on chip RAM, the memory. There is another memory interface which is off chip, right. So what is the difference between the on chip and off chip memory? The on chip memory is usually the cache or some other relatively small amount of RAM that is used just for storing data temporarily, right. Typically what is required of on chip memory is that it is very fast, meaning that once I give out a request, the response comes back very quickly. The flip side of that is typically it cannot have the same high density that DRAM does, right. So, the high bandwidth memory interface goes off chip to DRAM, which is typically megabytes or hundreds of megabytes, whereas the on chip RAM is typically in the kilobytes range. And of course, we have something called the DMA bus master. DMA is direct memory access. Like I said earlier, what it allows the system to do is, rather than the ARM processor, when it wants to transfer data from one place to another, rather than having to worry about reading in individual words and copying them into the destination, it can just tell the DMA master, go do some work, right, transfer data from A to B, and the DMA master will then take care of doing that. During that time, assuming that the processor does not need anything else that accesses the bus, the DMA can keep working, and the processor in its turn can work on something else. Okay. Now, we will see later how this can actually be useful, how you can have multiple masters sort of interleaving and sort of trading data or trading usage of the bus, so that the effective utilization of the bus is very high and each of the masters can be kept busy to a large extent. On the right hand side, the APB, the UART, that is the serial port, timer, keypad, general purpose input output pins, all of those are much lower frequencies than what we have on the left hand side, the AHB. Okay. So, this is a very generic diagram. All that it says is this is what a typical high performance bus based system would look like. Okay. So, now let us start looking at what a bus transaction looks like. Okay. And as far as the bus transaction is concerned, we need to essentially look at a lot of these timing diagrams. Okay. So, these timing diagrams are going to be common throughout the rest of this presentation. You can sort of figure out what is going on over here. Essentially what is being said is that you have a clock signal right on top, and the clock signal essentially is just a square wave, right, as you can see over here. And as the square wave sort of goes through its cycles, we have these vertical lines that are drawn over here that essentially indicate cycle boundaries. Okay. And what we are going to be interested in is there are a whole lot of other signals, control as well as data, and what are the states of those signals at the control boundaries. Okay. So, this is a typical very simple kind of data transaction, right, the simplest form of data transaction, bus transaction that can take place on a AMBA bus, right, the original version of the ARM AXI bus. What are the components that are involved over here? The signals that we are interested in, apart from the clock, of course, one is the address, then comes some control which we are sort of leaving blank at the moment, we are not going to mention what that is. Then there are these other signals, the HW data, the H ready and the HR data. Okay. So, one thing you would notice over here is, like I said earlier, the control, of course, we have not yet specified exactly what is going on over there, but presumably that takes care of including things like, are you trying to read or write, etc. Right. I am indicating a transaction where there is both HW data as well as HR data. Okay. Now, the interesting thing over here is you would need to keep in mind that effectively what we are doing is we are splitting the writing part of the bus and the reading part of the bus into two separate components, right. And in principle, at least according to this diagram, I can both write and read at the same time, because I have two sets of wires, one doing writing, the other doing reading. Usually that is not very useful because I only have one address. So, all that it means is I can write something into the same address that I am reading from. Okay. That is not a very common occurrence, but this is used only for illustration and to sort of tell you that yes, in principle it is possible to have writing and reading happening at the same time. From an implementation point of view, we just do it this way because it is easier to visualize things by saying that there are separate write and read buses, even though the diagrams, the high level diagrams that we draw sort of indicate that they are the same bus, right. In practice, they go through some tri-state logic and end up coming out as two separate buses inside the chip. So, what does this simple bus transaction look like? What you can see is there is an address phase during which the address signal, the address bus as well as the control signals are set to some values. Okay. Notice how the timing diagram is drawn. Essentially what it has over here is there is this portion where essentially we are saying that wherever it is gray, it is an unknown or undefined state, right? It is going through some transitions. So all that it's saying is after this first positive edge of the clock, the address as well as the control signals go through some transitions and will change their values to whatever we want for our transaction, okay? And once it becomes this solid white section over here, it means that the address and the control signals have stabilized. What happens? Nothing until the next edge of the clock, okay? At the next edge of the clock, the address is sampled, okay? So that's typically the terminology that's used. What we say is that the address is sampled by the receiver, either the bus interface or by the slave itself directly, right? Once the address is sampled at that edge, it is free to change immediately after that, okay? So the assumption is that whatever slave is listening, whether it be the bus interface itself or the actual slave interface, it has to sample the address and the control signals at the positive edge of the clock, and immediately after that those signals are allowed to change. Immediately meaning whatever, one hold time after that effectively, okay? What about, so the transaction itself takes place in two phases. There is this address phase and then there is the data phase. So what we said is I gave the address A and the control corresponding to that transaction over here during the address phase, and during the data phase, I will make HW data. This is done by the bus master, right? Whoever put out the address is also the one putting out the data over here onto HW data, and I will also put out a ready signal to indicate that, or rather no, the ready signal is actually coming back from the other side. So the HW data is coming from the bus master, the ready signal is sent by the slave, okay? And whether or not it was ready before, at this point after it sees a new transaction, it then has to decide whether or not it is ready. In this case it decides yes, it is ready and makes the ready signal high, okay? Some time after that it also makes the data on the read data bus, it sets it to whatever value it has found corresponding to this address transaction A, okay? And at the next clock edge after that, if I look at the HW data, the slave can capture this data at that clock edge. If I am talking about HR data, the master can capture this data at this clock edge. In other words, if the master is trying to read, then it would look at HR data. If the master is trying to write, the slave needs to capture the value of HW data. Either way, only if the slave has asserted HReady, that is made it equal to 1, does this transaction complete successfully, okay? What exactly does that mean? We will get to that in a moment. What happens if the slave is not ready at a given point in time, okay? But before that, let us just quickly look at what the structure of the bus would look like internally, right? Essentially what we are saying is I could have multiple masters, master number 1, 2, 3 and slave 1, 2, 3, 4. Okay, it does not matter, I can increase or decrease any of these numbers as I want. The point is this middle portion, right, which essentially corresponds to what I have broadly marked as arbiter with some signals coming out of it. And as you can see, effectively what that arbiter is doing is it is sending a select signal which decides which of these masters M1, M2 or M3 is going to be responsible for the H address signal that is coming out here, okay? And similarly, which of them is going to generate the HW data that comes out over here, okay? So you remember we discussed earlier that there are either a multiplexer or a tri-state approach can be used in order to implement a shared bus. The AMBA bus is designed around the idea that you use multiplexers, okay? Now in practice multiplexers themselves can be implemented using tri-state, so this does not actually specify how exactly you are going to implement it. This is only the logical view of things, okay? But logically the way to think about the bus is to say that there are multiple masters and the arbiter's job is to use a multiplexer in order to determine which of those masters gets to drive data onto H address as well as HW data. And on the return side there is the decoder right, which basically says which of these slaves is going to drive HR data. Okay. So, obviously, there has to be some signal that goes to each of the slaves to tell it, okay, you have been selected, now work. Okay. How does this multiplexing actually work? The masters go through the address and control mux. This decoder takes part of the address, right, part of the address is sent to the decoder, and that then determines the H select S1, H select S2, H select S3 signals. Okay. So, we already saw that is how memory mapped interfaces work. They take out part of that 32-bit address, maybe the top 16 bits, decide that if it matches something like 4120 etc., it corresponds to the GPIO bus, GPIO peripheral. If it is some other number, then it corresponds to the FFT peripheral, right, and therefore generates a select signal corresponding to that. On the, and this essentially is the other thing that happens, the decoder also has to do one more thing, which is that there are these, there is another decoder rather, not one which works off the H address, there is another decoder which comes from the arbiter, which essentially takes care of giving the grant signals, okay, to each of the masters. Now, what exactly is the grant signal and how is it used? Intuitively, the idea is very simple, it is sort of like a chip select for the master, right, effectively saying only when the grant signal is high, that master is allowed to drive data onto its output bus. Now, who decides that chip select, who decides the grant? That is the arbiter. So, with all of this in mind, let us just look at the pretty much the same data, the bus transaction that we saw earlier, right. The H address and control are set to some value A during the address phase, but now the difference is immediately after the address phase, the slave looks at the address, looks at the control signals, interprets what is being asked for and says I am not ready. It basically makes the ready signal 0. What does the master have to do? It does not have to retain the address and control signals, it can change them, right. But on the other hand, whatever it changes to, it now has to basically wait. In other words, if it was trying to write data, it has to make sure that that data signal remains high until the slave says okay, ready, and I accepted that data. So, nothing else can happen during this time. Okay. The master cannot just give up and say okay, I will do something else. I can't take away permission and give it to somebody else, right, or at least if I want to do something of that sort, then I need to be a bit more intelligent about how I do it. In this basic kind of structure, if the slave says no, not ready, that is it, the entire bus freezes, it has to wait until the slave becomes ready. Okay. But eventually we assume that the slave does become ready after a while, and the moment it becomes ready, then the very next clock edge after that, the data coming from HW data is sampled into the slave if you were trying to do a read, or the slave would have made sure that the data that is available over here is correct, and the master can then accept it. Keep in mind that at the previous two clock edges, even though there might have been some data at those clock edges, they are not considered valid data. The master should not do anything with them. Okay. So, it is very simple, just use this HReady signal and you can essentially insert wait states into the bus transaction as you want. Of course, what you need to be careful of is, if it is just implemented in this way, potentially one badly written slave, badly designed slave can effectively destroy a system by just pulling HReady low and leaving it there. The moment the master tries to talk to it, it will never get a response and it will hang over there. Okay. That can happen. In the past at least, there were situations where this was not even a very rare occurrence. It was quite easy to create something which could just hang the entire system. Nowadays people usually introduce a lot of other variations on the bus to prevent such things from happening. How do we extend this? We can go to multiple transfers, right. Now, the most simple kind of multiple transfers would have been finish one transaction completely, A and control is done, I get back the data and then start the next one. Obviously wasteful of time. We can do something called pipelining, right, where what we do is we just say that I will give out the address and control corresponding to A. I know that it will take at least one clock cycle to finish that particular transaction, but during the next cycle I will go ahead and say what I want to do next. I will give the address and control corresponding to B. Okay. One cycle later the data from A comes back. In the third cycle I have started giving the data the address and control for C, but my slave was not ready. Okay. So what happens? C just gets extended out by one cycle. The write data corresponding to B also has to be extended out, right. So all of those things, they just, it's pretty much intuitive. Whatever you would expect to see is happening over here. It's just that that ready signal becoming low automatically stretch things out by appropriate number of clock cycles.